My purposes for this video is to go through the electron configurations, review excited and ground states, and talk about electron configurations and how to fill up electron orbitals. So, without further ado, let's get started. So the first thing that we need to go through is this concept of the Bohr atom, Bohr. Uh, this is that two-dimensional ring system where you see electrons orbiting the nucleus, kind of like the planets orbit the sun. This type of circular orbit, it is a two-dimensional um, model, and there's no height to it. It's all in a circle, nice and neat, and that's not what really happens. However, we can still use this model for our benefit and to talk about some of the concepts. The first is being this whole bunch of ideas is that there are discrete energy levels, and the rings show this pretty easily. However, these energy levels, as we see in the orbitals, they translate pretty well to the three-dimensional model as well. The idea, however, is that the closer you are to the nucleus, or the smaller the orbital, the less energy is required for that electron to be in that orbital. A lot of it comes down to just the charges. You get that positive attraction force, which makes it easier to put that electron in there. Um, Electrons, and this is our jumping off point, electrons are lazy, which means that they do not like to spend energy. Um, a lot of chemistry comes to that concept of electrons not wanting to spend energy. It is known as stable. The more stable it is, the better. I think it's a pretty easy concept to comprehend. So lower energy is more stable, and it is a driving force for much of chemistry. And this is just really the first example we're going to see of this. The lowest energy state means you're spending the least energy to exist. The example that I used in class was the ground state is like standing on two legs. The excited state is like bouncing on one leg. And if you have enough energy, it's like you're hopping on one leg. More and more energy, more and more difficult. You would like to be in that ground state compared to standing on one leg for your existence, which is why electrons are lazy. They like to be in that ground state, which in terms of energy levels is closer to the nucleus, or um, in that lowest possible energy orbital once we get there to the 3D model. This idea of a quantum tells us that there are distinct energy requirements to go from one energy level to another energy level. And this holds true for the orbitals as well. So when we get to our orbitals here, which is my wonderfully drawn MS Paint version, to go from the 1s to the 2s requires amount of energy, just the same as going from n equals 1, the first energy level, to n equals 2, the second energy level. It requires a specific amount of energy in order to do that. It has to be that amount. They are exact amounts. Which is why when this electron eventually falls from the excited state to a ground state, the energy that is released is very specific, which is why you get a very specific color. You're not going to get some other color. It's going to be only one color, only this wavelength of energy that is released. So we saw this in our flame test lab, is that when you give that electron energy from, say, like a fire, it goes into an excited state, and when that excited state ends, it goes back down to the ground state, releases that extra energy as a photon of light, which is why we see color in the flame test. Now, obviously, this Bohr atom, the two-dimensional, it simplifies it, but if you can still have these types of electron orbitals where you would have an excited state. So just say we had an electron here, right? Going from the 4s to the 1s would release a certain and specific amount of energy. And if that's whatever enough energy it is, that is the color that you get. They are specific to each element. A lot of that math for why certain colors show is, we're just going to say, way above the scope of this type of course. All right, just want to make that clear as well. So I will not ask you, for the specifics, but just know that that is the general concept behind it. So we take this two-dimensional model and we can turn it into a three-dimensional model. And a scientist called Schrodinger starts finding out the relationship. Bohr had himself started this relationship, except his math only worked for hydrogen. So his math worked, but only when there's one electron. And a lot of that just boils down to the fact that electrons repel each other, which introduces another variable, and the math gets very complicated very quickly. So we start to see a whole bunch of this stuff. Schrodinger's equation. In the bottom right, there's Schrodinger's equation for hydrogen. So that's just one electron. The math when you add two electrons is insane. Long story short is that you get values that solve this equation, and you can have three-dimensional models of where electrons are in an atom. You cannot have the exact location. There's something known as the uncertainty principle. But you can know if you took a screenshot of this electron 1 million times and it's in this orbital, you will get a heat map that looks like this. That's the best way to explain it. This is not like a sphere, like a hard sphere of something that the electron has to stay in. It's just a heat map where you are very statistically likely to find the electron at any given moment in time. And the reason, just the math solves for this. You can, you've graphed lines in math class. You can graph a two-dimensional model. You can graph a trapezoid or a square or a triangle. You can graph that on a two-dimensional graph with an equation. Just like you graph lines with equations, you can graph a three-dimensional shape into coordinates as well with the x, y, and the z axis, and that equation is effectively what this is. Just for those that are interested. Um, Obviously, way above math that you're currently taking, which is okay. So, with that being said, this is where you're going to find your electron most of the time, in one of these orbitals. They have different shapes, different sizes. Um, they look like this. They have a number and a letter. So when I ask you for the orbital, I'll ask 1s, 2s, 2p, 3d, etc., and so on. The number is a general representation of energy levels. 1s is smaller and therefore less energy than 2s. There are examples where this is not the case. And this is a little bit of a special case, but if we look here, the 4s is actually lower energy than the 3d orbital, and that does get a little wonky, but when we start in our next chapter, we're going to talk about that a little bit, because it is relevant when we start making ions, and that's going to be relevant, pretty soon. So with that being said, the 4s is a little bit of a exception, but it gets weird. We'll talk about it. But generally, 1s, 2s, we see 3s, we see 4s, and 5s at the top. They're different in their energy. And then finally, so that's the number, just talking about size. 1s is lower energy, electron's going to fill it first. And then secondly, the letter, it discusses the shape of the orbital. There's a whole bunch of different stuff that we could get into. And if you look up other YouTube videos on this concept, you talk about something known as quantum numbers. I wanted to give us this more streamlined version just for the sake of getting through this material with the time constraints. Um, if you take AP chemistry or chemistry in a college setting, you will get more in depth into this. But this is just where I want to keep us for now. Long story short, the letter is kind of like the shape. There are four shapes: S, P, D, and F. Simplest to most complex. Generally, when I say simplest to most complex, that also means energy lowest to highest. 1s, if we go here, 3s, 3p, 3d. The 3s is a lot lower energy than the 3p. The 3p is lower energy than 3d. And that just goes to the shapes. The d orbitals look like, I say double clovers or double peanut. P for peanut, S for sphere. Makes it nice and easy. So Each of these orbitals, and this is the best way to explain this without going to these quantum numbers, is that they're suborbitals where they split off. And these are just rules that are generally make our lives easy, just to kind of go through them. The s orbitals have only just one orbital in them, and they start at 1s. So we have here's our 1s. That's the only one that has the number, the principal, the energy level of 1. Okay? P orbitals, they start at 2. There's no 1p. Again, I'm streamlining this instead of going to the quantum numbers, the math behind this. Each p orbital is split into 3 separate suborbitals. You might see the term shell, especially in some of the gizmos or other resources. I'm just opting to use suborbital just to make it that streamlining our vocabulary. There are 3 2p orbitals. One of them looks like this. One of them looks like this. One of them looks like this. And if you were to graph all of them together, it looks like this. Just to show you how in three-dimensional space, how they overlap. Because they kind of form like almost like a sphere around them, but they're just all 3 of them combined make this image. The d orbitals, they start at 3, which is why again we don't see a 1d or a 2d. Right here, we start right here at 3d. This is the first d orbital right here. There are 5 suborbitals in them. They look like this. Most of them, 4 of them are this double clover. One of them is a peanut and a donut. Again, it comes down to just the geographic or the geometric shape of them. Notice they're on different axes in the three-dimensional sphere, and then this one is just a little bit different. So one of them has a weird shape. The other ones are that double clover. And then if you are just curious about how the f orbitals work, the same pattern. Instead of starting at 3, they start at 4, and then there's a 4f, and there's 7 of them, and they have a whole wacky shapes here. They look like this. Just, yeah, you start getting some really weird shapes here with some weird, f 3xy minus y squared. Yeah, that's some wacky math there, which is why we're not getting into them. Okay. When we start to fill up these electrons or these orbitals with the electrons, each of those suborbitals can hold 2 electrons. One of them goes like this, again on the camera, clockwise. The other one goes counterclockwise. Okay? Or up and down is the term that you will see. And the way that we write this in our orbitals, we would have one that goes up and one that goes down like this. Okay? If you draw them like this, like full arrows, I'm not going to take off on that, but just the notation that we will most commonly see looks like this, with that little half arrow. So, there are 3, oh, well, let me get through. Each of these suborbitals, just an example, here's our 2p, 2 electrons here, 2 electrons here, 2 electrons here, 6 total electrons, okay? So, the rules for this is that you basically need to take how many electrons are in your atom and start filling them up from the bottom up. Because electrons are lazy. The ground state, so using that term from before and adapting it to our new situation, the ground state is the lowest possible energy. And in our table here, you'll see this arrow. This is more energy. The 5s orbital is more energy than the 1s. So this electron is going to start in the 1s itself. Okay? There are the 3 rules. Rule number 1 is that in each orbital, one atom or electron must go up, one electron must go down. So you cannot do it like this. You have to have one that goes up, one that goes down. Rule number 2, or rule number 2, is that in order to be a ground state, you must be in the lowest possible orbital. All right, ground state electrons do not go in a higher orbital until it is filled. So here is our 1s. We filled this up. The second electron is not going to go here. This is an excited state because there's still a seat open. There's still another electron that can fit into this lower energy orbital. So it's going to do that first because it is less energy and electrons are lazy. it will pair up first. Now, if we were going to add another electron, now that this is full, you can only have 2 electrons in there. Now that this is full, this 2s becomes the most energetically favorable, the lowest energy, so you're going to fit an electron here. And then you would pair up. And then our final third rule is that when you have electron orbitals, when you have suborbitals, where there's more of one of them, you want to distance them, fill up each of the suborbitals first before you start to pair them up. And this is because electrons repel each other. So that repulsion is a little bit of extra energy, and electrons don't want to spend extra energy to be next to one another. So only when they absolutely have to are they going to pair up. So we fill up 1, 2, 3. Now that these are full, now you can start to pair them up with any extra electrons that you have, like this. Only once this is done. Okay? So those are the rules, and I go through just a little bit of them. The amount of electrons depends on whether or not it is an ion. The base rules, and you will get a periodic table, and you need to know this, is the atomic number is the amount of protons an atom has. Additionally, in a neutral atom, so that is not an ion, the amount of protons equals the amount of electrons. I'll write this up here. In a neutral atom, a neutral atom just means it is not an ion, there's no charge on it. So fluorine has 9 electrons. Neon has 10 electrons. Scandium has 21 electrons. And those are the number of electrons that you're going to start to fill up this chart with. So right now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the electron configuration, or the orbitals for neon, 10 electrons. I gave this to you in your lab, and I will probably give you some basic ions. Probably just, instead of, I gave you, I think, lithium plus. So I would probably give you something that's relatively smaller, or I might give you, fluorine minus or something like that, where the charge, and here's our just general formula, the charge equals, I'm just going to use the letters protons minus electrons. So if I give you fluorine minus, and I say that the charge is -1, and you know that there are 9 protons, you would need to algebraically solve for this, and you get that E equals 10. So there would be 10 electrons to fill up your orbitals with. So this would be the electron, so this would be for neon or fluorine minus. And we will talk a little bit, not a little bit, we'll talk a lot about why this is significant that they share. Pretty much straight first thing in the next chapter. We're kind of splitting electron orbitals and electron configurations up into 2 chapters. So this is the, what you would fill up for pretty much any atom that has 10 electrons would look like this. So if I give you, additionally, if I gave you sodium plus, sodium plus also has 10 electrons. That's on there. So this would also be, or Na plus. All of these atoms all have 10 electrons. There's a reason for that, which we're going to get into. Okay? So those are the rules for just generally filling up orbitals. The last thing that I have, and I just want to go through, is the last thing that I want to get through is just what is known as the electron configuration, which is how we write it off. I do just want to say quickly, I did include this, just configuration of ions, what this would look like. Okay, I think I talked about this exception. We're gonna talk about this exception actually more in chapter 4, just at the very beginning. We're really gonna just, the first week is gonna be more electron configurations, really. talking about the exceptions, the role of the periodic table, which I hinted to in our lab. So we're going to really talk more about that. Not my expectations. My expectations for this upcoming test is to be able to do this, do something like this, where it's a simple ion, because there's ions that are not simple. We're going to get there. Um, and to write the electron configuration. So the electron configuration, all you really do is just create it's a list of the orbitals and how many electrons are in there. So you start with the lowest energy, 1s, right? This is the name of the orbital, and there are 2 electrons in it, so we write a 2 as a superscript, not a squared. And when I say this verbally, I would say this is 1s2. I'm not going to say 1s squared, I'm going to say 1s2. Then we move on to our next orbital from lowest to highest energy, 2s, 2s, and there are 2 electrons in there. And then we move up to our next one, 2p6, because there are 6 electrons in there. Now let's just say I added in another electron like this, then it would just be 3s1, 1 electron in there. And you can get all kinds of wonky stuff when you really start adding in electrons. Something that looks like this, and I'm also doing the correct ordering of this too. I just want to show you like this. So now we have 3s, and there's now 2 in here, 3p, and there's 6 electrons in there. We go up to 4s, and there's 2 electrons in there, and then we count 1, 2, 3, 4, 5, 6 electrons in the 3d. Okay. I also might ask you to identify this element using stuff that we've kind of gone through. And you could count the electrons. 1, 2, 3, 4. 4 plus 6 is 10. 10 plus 2 is equal to 12. 12 plus 6 is equal to 18. 18 plus 2. Oh, this should not be 10. I'm sorry. This should be 6. This is 20. And then 20 plus 6 would be 26 electrons. Right? So if there's 26 electrons, well, let's go to our periodic table and we find element 26. This would be the electron configuration of iron. Alright, using that concept that how many electrons are in there would help you identify what element this is. So this is a good test question as well, using the concept of how many electrons are in there to solve for what element it is. Okay? So that's really my expectations for this test, is being able to fill this up and to make conclusions from it. You know, as with all tests, I give you some kind of application of this, but I think it is doable, that you need to be able to fill this out and use this information with the new information to solve some type of question. Okay?